these lectures, we are going to talk about time response again, but this is part 2, which is specifically focused on the second order system. Okay. So what we're going to cover today is only 4 things. In every online lecture, I promise that I'm going to cover you only four elements. Okay. Okay, that's okay. Okay, so we're going to talk about the introduction to second order system, and then we're going to talk about, I'm going to introduce you the general form of second order, and then for the second order system, what are the specifications that you need to know in order for you to evaluate the performance. And then lastly, we're going to talk about the second order transfer function via testing. Okay, I did this lecture for the ZK50, so this is on for ZK for another class, but it's no harm for you to listen it again for this lecture. Okay, so what is yesterday in our previous lecture we talk about first order system, right? So in the first order system we talk about the general form of first order system, which is the transfer function is A over S plus A, and we talk about the system response shape for the first order system, right? So the system response shape is for the first order system is like this. Okay, the system response shape, PT inside. Okay, and then we talk about the time constant, which is the key element for first order system is the time constant, which is the definition is it has to be 63% of the final value. So that is for the first order system. Okay, and also we talk about the performance specification for first order system, which is the rise time and also settling time. Okay, now we're going to extend our understanding for second order system. Okay, so similarly, we're going to talk about the general form, what are the system response shape, and what are the performance specifications for second order system. Okay, in our normal system, the system that we usually deal with is actually a second order system. When you are doing your FYP later on, you will normally deal with a second order system. If the system is very complex, for example, you are dealing with precision control of quadrotor or underwater projects, but we still can assume that the system is a second order system. Okay, so for second order system, okay, we have many types of system. Okay, but in general form, the second order system is the transfer function is B over S squared plus AS plus B. Okay, so unlike first order system, you only have one type of first order system, but second order system, we have 4 types of second order system that we need to know. Okay, so let's go one by one. The first one is the overdamped second order system. So the transfer function for the overdamped second order system is in the textbook is 9. Oops. Okay, is 9 over S squared plus 9S plus 9. So this is the kind of transfer function for second order system. Okay, so for underdamped system, the transfer function is 9 over S squared plus 2S plus 9. So this is for underdamped second order system. And for the critically undamped second order system, the transfer function is 9 over S squared plus 9. And if the second order system is a critically damped, it means that you're going to expect the transfer function, the numerator, the denominator will be some kind like S squared plus 6S plus 9. So if you see here, the difference is at the denominator. Okay, as you factorize the denominator, you're going to have, for the overdamped, you're going to have a real poles. Okay, for underdamped, you're going to have some real and imaginary poles. For undamped, you're going to have an imaginary poles. And for critically damped, you're going to have a pole at the same place. Okay, so let's look at the pole zero plot for overdamped, okay, underdamped, undamped, and critically damped. So for overdamped, for if the second order system gives showing an overdamp response. Okay, so the poles based on this numerator denominator, you're going to expect that the poles is at you're going to expect that the poles is somewhere sorry about that. Okay, hold on. Okay, so for overdamp response, the poles will be, the location of the poles will be at two different locations, which is 1, 2. So when you factorize this, you're going to expect that you're going to have two poles, which is the location of the poles is at the real parts of the S plane. It means that S plus pole 1, S plus pole 2. So the first pole will be S equals to minus pole 1 and minus pole 2. So the plot of the poles at the pole 0 plot, it will be pole 1, pole 2. Okay, so how about the underdamp response? So for the underdamp response, you're going to expect to have, if you factorize this pole and you get the pole is equals to real plus imaginary 1 S plus real minus j imaginary. When you get this kind of results, okay, you know that you're going to expect that this is an underdamp response. Okay, so the pole's location is plus here at the real part, the same real part, and minus here. Okay, so this is for underdamp response. Okay, so and for undamped response, what you're going to expect is you're going to expect that when you factorize this numerator, you will have an imaginary. Okay, so when the plot is somewhere in the imaginary line, so and for the critically damped response, you're going to expect that you're going to have two things. Okay, when you factorize it, you're going to have the same pole value. So this is critically damped response. So what it says here, when you are given a transfer function, okay, at this form where the numerator is a constant and the denominator is in the form of s to the power of 2, okay, we should know that you can expect that it is a second order system. We can assume that it is a second order system, and we can factorize the denominator, and the poles, the value of the poles that we get, we can estimate the kind of response that you will going to expect. Okay, so lastly, second is on the response. For the overdamp, okay, the kind of response when you have an overdamp system with the two poles at the real parts, the kind of response is like this. Well, you can refer to your textbooks. Okay, so it should reach somewhere at the desired point that you want, but this is we call overdamp. So for underdamp, you're going to expect that, okay, you have some desired point here, so you're going to expect that your response will be like this. Okay, so there is some, what we call here, and some overshoot, and then it's some oscillating before it goes to the desired set point. Okay, for if the system is undamped, so this is very dangerous. So you have the desired point here, okay, one, but the system is oscillating. So what does this mean? I will discuss later. Okay, for the system is critically damped, it means that it is almost similar like overdamp, but this is very theoretical. This is very ideal conditions that is rarely you get for the actual system. Okay, so Imagine I've discussed with you the antenna position control system, right? So you can imagine now, if you want to control the position of the antenna to move to the desired angle, okay, for example, you have the antenna at 0 degree and you want the antenna to face 90 degree. Okay, so you have the control system, and you will see that the antenna, when you give the desired point 90 degree, the antenna will move, the whole dish will move 90 degree. So the movement of the dish, if it is an overdamp response, you will see, you're going to expect that the dish will move very slow until it reached 90 degree. Okay, so the performance of overdamp response is like the first order system. So it's slow. Okay, so sometimes we need the antenna dish to move fast, right? So we may need usually an underdamp response where it will move fast, but the problem with underdamp response is it will have some overshoot. So instead of it's move fast, but the setback is it will move another angle, it will move above 90 degree, for example, like 110 degree, and it will swing sometimes before it reach to the 90 degree. So when you're talking about safety, okay, when you're talking about safety of humans around, and also when you are talking about cost of the device, okay, so those are the oscillation part here is something that we need to control. Okay, so if it is an undamped response, now you know that this is very, very, very dangerous, and we don't want it to happen. This is the worst thing that we as a control engineers, we don't want it to happen. So what it means here is that the from 0 to 90 degree, it will move, but it oscillates between, for example, 100 to 80 degree, 100 degree to 3 degree. So this is things that we avoid. So for critically damped, usually this is an ideal system. Okay, so the whole things here that I explained is actually in the table 4.7, figure 4.7 that you can see here. Okay, so next one. If we combine the whole these four kind of systems, okay, so you can expect that the step response for second order system, you can expect four kind of response. Either this is undamped, underdamped, critically damped, and overdamped. Okay, so yep, we are talking about, imagine if we have an elevator system, another system elevator in our best study buildings. So usually we don't want a system that is overdamped because it's going to take some time to reach level 10, for example, right? But we hope that it's good if we can have the elevator a critically damped system. It means that yep, it goes to the level 10 at the much faster compared to overdamp. But okay, but what happens if it is under dam system? Well, if it is under dam system, it will reach the level 10 much faster, but it has some oscillation here where it can swing you to level 11 first and then go to level 10. Okay, so undam is something that we don't want. Okay, so usually in control design, in control designing a control, we are looking at under dam system. We are trying to control the under dam system so that it won't overshoot too high. So this is what we're going to discuss in the further chapter. Okay, so what is under dam system? Okay, let's look again at the transfer function for under dam system. Under dam system, the kind of transfer function we're going to expect is the denominator is s squared plus 2s plus 9, where when we factorize this, we're going to expect that we're going to have a poles, there is an imaginary part and also an real part and also an imaginary part, right? So it is like this when we plot and explain. So when we have the system that the poles is somewhere in between in this area, you know that you're going to expect that it is an underdamped system. Okay, so what is underdamped system here? Actually, what happens actually is that the one here is the uh, force response. Okay, so for the force response here, and the remaining here, the natural response, but it has a damping element here. Okay, so it has some damping element, which is the exponential decay generated by the real part of complex pole, and the sinusoidal oscillation generated by the imaginary part of the complex pole. Okay, so for next Okay, there is some exercise first you can do. Okay, so write the form of the step response for the system. So the first step is you have this transfer function of the system. So it is 200 over s squared plus 10s plus 200. So what we do first is we factorize the denominator. So when we factorize, I think you get s plus 10, s plus 20, if I'm not mistaken. Okay, so it will be the first pole you're going to expect that it will be minus 10, and the second pole is minus 20. So at the poles, at the S plane, you can expect that it is minus 10 and minus 20. So what is this? You can refer to the tables and you can note that it is an overdamped response. So what is this? So this is when you know that you can expect that this transfer function will give an overdamped response. Okay, so simple exercise. Okay, now let's look at the general second order system. So what we are focusing on for control engineering is on the second order system. Okay, we want to control the performance, the response of the system so that it won't oscillate much and it goes to the desired set point as quick and as smooth as we can control. Okay, so before that, you need to learn some theory of the general form of second order system. Okay, so theoretically, the general form is second order system is actually equals um, to the natural frequency squared over s squared plus 2 times with the damping ratio times with the natural frequency s plus with the square of natural frequency. So there are two elements in the second order system, which is the natural frequency and also the damping ratio. So the natural frequency is the frequency of oscillation of the system without damping, and the damping ratio is the exponential decay frequency of the envelope to the natural frequency. So let me reverse back here. So this is the kind of like natural frequency, the frequency that we are of the system, and this is the damping ratio, the amount of damping. Okay. So damping ratio in by equation, it is an exponential decay frequency over the natural frequency, which is the real parts over the natural frequency, which is A over 2 over with the natural frequency. Okay, another exercise here. Okay, so if you are given a transfer function, which is 36 over s squared plus 4.2s plus 36, okay, you are trying to find the natural frequency and the damping ratio of the following transfer function. So let's do it together. Okay, so you know that this is a second order system because it has s to the power of 2. And so you know that the general form of second order system in the form of natural frequency and damping ratio is equals to natural frequency squared over s plus 2 times with damping ratio, natural frequency s plus the square of natural frequency. So from this, it's so straightforward. Okay, you can just find your natural frequency, which is 36, square root of 36, which is 6. So to get the damping ratio, which is equals to 4.2. So the damping ratio will be 4.2 divided by 2 times 6. So you get your damping ratio. Okay? Any questions so far? Any question? No?
No, ma'am.
Okay. So by the way, what was the damping ratio? Can someone help to calculate it for me? 0.35.
35.
Okay, thank you. I just want to hear. Okay, all right. So this is the damping ratio for this. This is the damping ratio for this transfer function. Okay, from the damping ratio, actually, if you are given the damping ratio for the second order system, okay, you can actually predict the kind of response. Okay, so this is the damping ratio, and this is the pulse and the step response. So if you have the damping ratio 0.35, okay, so it is in between 0 and 1, you're going to expect that the system has two poles, which is at the real and imaginary part at this area, okay, which has the real parts and imaginary part, and means that it is an underdamped system. Okay, so again, if you have the damping ratio 0, then you know that it is, you're going to expect that it is undamped system. So imagine that there is no damping ratio. So it means damping ratio 0. So it means that it's oscillating. What it means that, imagine like a car where you don't have, imagine like a spring. Okay, it has damping ratio very, very, very low or 0. So it means that it keeps on oscillating and oscillating, oscillating. To make it not too oscillating, you need to add some, pendulum. Okay, so to make it not oscillating, you need to add some spring to damp the oscillation. That's what it means for damping ratio. So the amount of damping ratio we determine we control the damping of the system. Okay, which is very important in control. Okay, so if the damping ratio is from 0 to 1, then you're going to get under damped system. But if you have damping ratio that is 1, which is it will make the system to be critically damped. Okay, and if the damping ratio is more than 1, it means that it's too high damping. What will happen is that you make the system, the response stiff. Okay, so it will go from not really flexible, so it will create an overdamped response. Okay, so the damping ratio plays an important role in a control system, in a system, second order system. Okay, another exercise here. Find the damping ratio and identify the kind of response expected for the following system. Okay, so look at again this one. So you know that everything here is a second order system, right? Second order system, second order system, second order system. So the first step is, we can just write the general form of the second order system again. Plus S squared plus 2 damping ratio, natural frequency S plus net frequency squared. Sorry about my handwriting. Okay, and from here you can find the answer for each. The damping ratio for A, what's the damping ratio? For B, and for C. Okay, so it's you can try to calculate it, okay, and give me the answer for A, B, and C. What's the answer for A?
For A, 1.15.
1.15. For B?
1, ma'am.
1. For C?
0.85.
0.85. So, in your opinion, which system is worth to control? Which system is the best?
B.
B, ma'am.
B. Okay, so
B,
because why? Why B?
Critically ideal.
Critically damped.
Critically damped. So how is the kind of response for critically damped?
The value constant.
Okay, so when it's critically damped, it means that the transient response is fast, then right, and it reached the steady state, right? But if you have a critically damped system, there is no need to control the system anymore. It's a perfect system. In real life, do you think you should be able you can get this kind of perfect system? Which is actually not really. It's not easy to get the perfect system that can give a perfect response like critically damped. Okay, so in real life, what we want to control as a control engineer, what we are desired is the damping rate. When the damping ratio is less than 1, okay, so this is an underdamped system. So this is our task as a control engineer, to control a system that is underdamped. Okay, so okay, I have another 10 minutes. Okay, so what are the specifications for underdamped second order response? Okay, when you have an underdamped second order response, let me draw it here. Assume that this is and under them second order response, there are things, specifications that we need to know, okay? We need to know and in order to evaluate the performance, okay? The first one is the rise time. Okay, so for under dam response, you need to know the, when you have a system that is under dam, so you need to know the rise time. What is the rise time? It's the time required for the waveform to go from 0.1 to final value 0.9. Okay, so this is the final value here, final value. Okay, so the time from 0.1 here until it goes to somewhere 0.9 here. Okay, so this is rise time. The peak time is the time required to reach the first or maximum peak here. So this time we need to know the peak time. So the percent overshoot is the amount that the waveform overshoots the steady state value at the peak expressed as percent overshoot. So how much is the overshoot is the things that we need to know here, because later on we need to control the amount of the shoot to make it smaller. Okay, so the settling time is the time required for the transient dam oscillation to reach within 2% of the steady state. So we're talking about somewhere that between this we have the desired one. Okay, so somewhere 2% is 1.02 or 0.98. As long as these things, the response reaches somewhere in this area, then we can put it as a TS, settling time, the time is settled. Okay, so we always remember these 4 elements when you are talking about controlling a system. First, you have to assume that it is a second order system so that you are able to use the parameters, the 4 parameters here to evaluate the performance for your system. Okay, so these are the sketch, these are the real, the nicer, decent sketch for what to, about the rise time, peak time, settling time, which is 2% here. Okay, settling time, and also the rise time and peak time. Okay, so for a second order system, when we are controlling second order system, we are more concerned about the transient response. All this here up to this level, here, these are, we call it a transient response. Yeah, I'm going to draw it up here. Transient response. So that's why we have this chapter. That's what I'm lecturing for today, and yesterday is about transient response. So the parameters for transient response is rise time, peak time, and settling time. The next one is we need also to concern about the steady state. Okay, so what we say here is that how much errors is reduced. So when we are talking about controlling a very high precision, we want to control the system to make it more precise, then we really concerned about the steady state performance. Okay, so next, how is the formula for the peak time percent evaluation? The peak time is equals to this formula, which is pi over natural frequency multiplied by 1 over damping ratio squared. Okay, so then the percentage overshoot, there are 3 formulas that you need to know how to use it, okay, in order to get the percentage overshoot, which is the first one involving the, when you have an output response in terms of graph, and you need to find the maximum value and the final value, and you can find the percent overshoot. Also, if you have the damping ratio, okay, you can also find the percent overshoot. Also, if you have the from the percent overshoot, you can twist to get the damping ratio. Okay? So next is the settling time. The settling time is equals to 4 over damping ratio times with the natural frequency. Okay, and also a rise time. So the rise time is really, you have to refer to this table to find the rise time, okay, which I will not really discuss here. Okay, so some exercise. So you're given the transfer function 100 over s squared plus 15s plus 100. Okay, so find the damping ratio, natural frequency, settling time, peak time, and percent overshoot. So usually in the assessments, final exams, if you look at the past year papers, these formulas will be given. Okay, but it depends. The tricky part is it depends on what formula is given for percent overshoot. So you have to be alert. The 3 formulas in percent overshoot, because settling time and peak time is having the same formula, but for the percent overshoot and damping ratios, there are few formulas that you need to know how to use it. Usually in the final exams, it's not going to give you the whole formulas. Okay, so look at these questions. Okay, you know that this is a second order system. The first thing, always check first the system whether it's second order or it could be a first order. So as you know that it is second order system, and you can use, then you can try to find, you can start to find the natural frequency, the damping ratio. Okay, so first step is put the general order of the damping of the second order system. Okay, so from this, you should be able to find the damping ratio, the natural frequency, and using the formula, you should be able to extend to get the settling time, peak time, and percent overshoot. Okay, well, this one you can do it yourself at your own time. Okay, so similarly, another example, exercise 5. Okay, you are given the transfer function 361 over s squared plus 16s plus 361. So similarly, find the damping ratio, natural frequency, settling time, peak time, and percent overshoot for the system, and sketch the output response. So at the end of the day, at the end of this exercise, you need to be able to sketch the output response. Okay, so you know that this is a second order system, for example, so you can expect that the output will be some overdamp here and some oscillations and before it reach to the steady state. So based on your result of TS, TP, then you can plot here so you can see the whole response. Okay. So another part is the last one is second order transfer function via testing. As I said, like in the first order system, it's not that you can easily, if you have like antenna dish control system, it's not easy to get to develop the mathematical model for the system because everything is in a box. So that's why we call it black box. It is manufactured and is contained, the circuitry and all the things is contained in a box. Okay, but from the antenna position control system, we can get the performance. For example, we set the desired angle and we let the antenna move to the desired angle and we record the output response. So from there, we can evaluate the shape of the output response. Okay. So if you get a critically damped response, you are so lucky. That means that it's a perfect system. But remember that as the antenna is being used for ages, for years, it will be aging. The hardware parts will be, there will be wear and tear on the hardware parts, on the gears. So those elements, those things, and with the contribution of the weathers outside, okay, and with the atmosphere, those things will degrade the performance of the system. So when it decreases the performance of the system, when you look at the system performance, okay, after like the first when you receive it, it's a brand new, so it might give a perfect system, critically dense system. But over years, for example, like after 5 years, when you check the system out response, it will give, you're going to expect that it will give something like underdamped response. Okay. The worst is if it's not working, that it will give a undamped oscillating response. So that's what we don't want. So it's easy to see physically that this is not working antenna. But if we see that, oh, what happened to this antenna? The performance is getting sluggish. What happens? Okay, so I think we need to adjust something in the controller. So how do we do? First is you get the output response of the performance of the antenna. So what do you do? Okay, you set the desired point and then you measure, you measure the output response. So if it's angle, so you measure the angle. So you're going to expect that you're going to get something like underdamped response. So from the underdamped response, you specify the performance. Okay, so you specify the performance, which is TS. From the output plot that you can get your TS, you can get your TP, okay, you can get your TR, and then from here, you can get your damping ratio. Okay, when you get this one, you can get your damping ratio, you can get your natural frequency, and from this one, then you can develop your transfer function, which is, you know that it is natural frequency squared plus 2 squared plus 2 damping ratio natural frequency squared